We have one more lesson dealing with permutations. And then we're going to move on to combinations tomorrow. And then on Thursday, we're doing the binomial theorem. What we're looking at today is a little more practice with restrictions, but then we're also looking at repetitions, and you'll understand what that is about in a minute, and pathways. And sometimes it's called repetitions, sometimes it's called indistinguishable items, meaning you have some items that you can't tell the difference between. Sometimes it's called identical items. This is not a long lesson in terms of examples, so today will be your opportunity to go back and practice any of those permutation problems, as well as, I think there's 5 or 6 pages of permutation problems after this lesson that I've given you, if you want. So we're going to be finding the number of arrangements of items if items are repeated, which means they're identical. And we're going to continue to solve permutations problems. So let's imagine that I have 3 Snickerdoodle cookies. And I don't know if you can tell, but they are perfectly identical, right? In reality, they are not, right? They all have little imperfections. But I want to impress on you that they don't have to be perfectly identical, but I want you to think of them as identical. And I have 2 M&M's chocolate chunk cookies, and I have 4, I guess, chocolate chip cookies. So that's a total of 9 cookies. And I come home, and I've had a really bad day, and I open my cookie jar, and these are the 9 cookies that are in there. And I say, you know what? Screw it. I'm going to eat all 9 of these cookies. That's just the kind of mood I'm in. I know I shouldn't. I'll regret it later, but I'm going to do it. How many ways could I eat those cookies? This is the question we will be able to answer after today's lesson. And I'm not talking about, you know, if I eat this cookie first and then this one, that's different if I eat them in the other order. I'm talking about how many different ways can I eat types of cookies. And I could, being the kind of analytical, organized person that I picture myself as being, which is not always the case, I could eat them. There's my Snickerdoodles, there's my M&Ms, there's my chocolate chip. I could follow this order. I could eat chocolate chip, chocolate chip, chocolate chip, chocolate chip, M&M, M&M, Snickerdoodle, Snickerdoodle, Snickerdoodle. Personally, I wouldn't do that. I like a little bit of variety, because by the time I get to my 3rd chocolate chip cookie, I'm done with chocolate chip for the time being. But if I change the order of these letters, so I'm arranging 1, 2, 3, 4, 5, 6, 7, 8, 9 letters, and normally you would say 9 factorial. But if I calculate 9 factorial, which is some number, it doesn't matter, and I say, you know what, I'm going to go back in time and I'm going to switch these 2. That's not a different arrangement, is it? So of those 9 factorial, there are a whole bunch that aren't actually different. But this would be a different order, right? Variety, variety, variety. And I got to eat 2 chocolate chip in a row somewhere because there's more of them. So this would be a situation where we would have identical items or repeated items. If I had these 11 vehicles, and I know that if you had these 11 vehicles on a car lot, they are different. They have different vehicle identification numbers. Okay, they might have different options. But I'm talking about the colors. How many ways could I line up these cars in a row so visually I get a different arrangement each time? This would be one, right? I could line up the 4 blue and then the 4 red and the 3. It's not really pink, it's more magenta, but whatever. And if I change the order of those letters, I may not get a different arrangement if all I do is I take 2 of those blues and I just switch them. You know, my boss says, Paul, go out there and change the display. We don't like it. And I take this blue car and I move it and I put another blue car there and I switch them. I may not get fired, but I might get a warning, right? That's what we're dealing with. So we're going to do a bit of review first. How many ways can all of the letters of the word oranges be arranged if there are no restrictions? By the way, all of the letters in the word oranges are different. So this is a piece of cake. Isn't it 7 factorial? Did I count my letters correctly? So it's 7 factorial. I'm curious, if I say to you, how many ways can I arrange all of the letters if the first letter must be an N, how many of you immediately just say, Well, it's 6 factorial. That's a 6. See, what I do is I say if the first letter must be an N, I'm not even going to worry about the first letter. I'm just going to ignore it. And I'm going to arrange all of the letters of the word oranges. I'm going to ignore the N, and that's 6 factorial. If you don't think that way, then what you're going to have to do is use the fundamental counting principle. 1, 2, 3, 4, 5, 6, 7. This must be an N, so you go 1. I mean, even if you do take this approach, I think at some point, maybe right here, you say it's going to be 6 factorial. But for completeness sake, all right, no problem. How many arrangements of all of the letters of the word brains are possible if the letters B, R, N, and S must be together? We have done this question. I would say 4 times. It's Joan and Emily, except it's not Joan and Emily, it's 4 items. What we are doing is we are arranging these 1, 2, 3, 4, 5, 6 items, but we're doing it this way. We're treating this as a single item, BRNS, and we're treating the I as a single item and the A as a single item. 1, 2, 3, 4, 5, 6. And if I want to arrange or write all of the arrangements, there's 2 things I need to do. Bobby Bear needed to put on a pair of pants and a shirt. I need to arrange the 3 items. There's 3, A, I, and the BRNS. And I need to arrange the 4 items within this. And I don't think you need to write all of this. I'm just being clear, in case somebody wants to look at it later and look at exactly what we're doing. So this would be 3 factorial, and this would be 4 factorial. Notice I didn't feel the necessity to, where I wrote 3 factorial, I didn't feel the necessity to go 3 times 2 times 1. You certainly could do that. You can go 3 times 2 times 1, times 4 times 3 times 2 times 1. But you can do it this way. 3 factorial times 4 factorial. That's 6 times 24, I believe, is 72. Is it? It's not? Thank you. It's not 3 times 24, it's 6 times 24, which is 144, Kaylee? Okay. Example 3, how many arrangements of all of the letters of the word pitcher are there if the vowels must be together? Well, it's Joan and Emily. But the reason why I'm giving you this question again is the following. I should be able to ask you this question, and you have to know that you have to answer the first question I'm not asking you. Because the only way that we can find out how many arrangements have the vowels not together is to find the total number of arrangements with the vowels together and take it away from all of the arrangements. So that's why we're doing this first question. But on an exam, I don't think I would feel the need to lead you along here. The vowels must be together. These are the 2 vowels, and then we have a P, a C, an H, a T, and an R, I think. I better double check that. P, I, T. Yeah, that's right. So I'm arranging 1, 2, 3, 4, 5, 6 items, kind of in a very general sense, and I'm arranging those 2 vowels. Whatever that number is, and I believe it's going to be 1,440. Thank you. That's how many arrangements have the vowels together. On the other hand, 1, 2, 3, 4, 5, 6, 7, 7 factorial is the number of arrangements, period. I don't know what that is. Is that the 50-40? Okay. So this is 1440. Yes. This is 5040. This is not our answer to part B. This is the total with the vowels together or not together. A little sloppy with my writing there, but that's okay. You know, this is, like I said to you yesterday, day before maybe, I don't know. I got a whole stack of Post-it notes and I start writing down all of these arrangements, and like some kind of crazy person, I just paint the walls with all 5,040 of these. Some of these 5,040, the vowels will be together. And we know that there's 1,440 of them where they're together. Some of them will not be. Well, that would be the difference. They're either together or not. So if I subtract this number, I get the answer, and unless my math is totally off, I get 3,600. Once again, before we go on, you know, question B would be the question I would ask you. I wouldn't lead you on and tell you how to do it. Any questions with number 3? So some classic kinds of scenarios. All right, warm up. How many unique arrangements, that means different, don't be fooled by the word unique, of the 4 letters of the word past are there? Well, that's so simple. It's 4 factorial, right? Which is 24. And you don't have this in your handout, but because I don't have a life some evenings, I listed them all. These are all 24. No matter what you do with those 4 letters, you cannot get a 25th one that's different. And there's kind of a system that I used here. My first row is all starting with P, and I took care of the P followed by the A first, and then the P followed by the S, and then the P followed by the T. And I went through and did that. Actually, it's been so long, I probably typed it into a website and it gave me all the arrangements. But there's 24, and that's not a difficult question. But the next part of this warm-up says, how many unique arrangements are there of the 4 letters of the word pass? And now what we have are 4 items, but 2 are identical. So if you come up with, well, I'll show you. Here are the 24 arrangements of all of the letters of the word past. And every highlight is a T. Okay? But there's no T in the word pass. So what's going to happen is all of these T's, when I go from the item arrangements for past, when I go to pass, all the T's will become S's. And if you take a look at that, for example, these first 2 are going to be identical now, aren't they? It's going to be P-A-S-S, P-A-S-S. So those 2, because the T and the S are in different places, but I'm going to make them both S's, those 2 become 1. And that's going to be the case with every pair where T and S are in opposite places. So for example, that one and this one. These 2, right, they're different right now. But if I make those T's S's, they're going to be the same. And that's what I'm going to show you right now. I've changed them all to S's. And now what happens is you have these 2, which used to be different, and now they're 1. And I'm not going to go through and do the whole thing. I also have asp and asp, and before they were different. And I will be able to pair them off, and what that means is that there are half as many. I mean, I could go through and do this. Already counted here. Already counted. already counted. I'm regretting doing this already, but I've already started. Asps, apps, spa, saps, sasp, sasp. How am I doing? You having fun? Sap, spas. I was going to say spas, I'm down to 12, okay? Now, what if it's not past with 4 different letters, it's not pass with 3 different letters, it's sas with 4 different letters? How many of you know how many arrangements there are going to be without even me showing you? It's going to be 4. The only thing that can move is the A. It can be in the first, second, third, or fourth. But here's pass, right? We're already down to 12. All of those P's are going to become S's. So I have sas. I should have one more. No? There it is. Come on, you guys, help a fellow out. I have ass. Okay, ass. I have, you get the idea, right? I'm not going to go through them all. What's going to happen here is you will only get 4 unique arrangements. Everything else in this list is included in one of those 4. So the answer to this question is 4. Now 12, the answer to the previous question, is not a factorial. And neither is 4. But there is a connection between this. Between the number of arrangements of all 4 items when they're all different, which is 24, and the number of arrangements when 2 are identical, which is 12, and the number of arrangements when 3 are identical, which is 4. So the question is, what do you believe the rule is? What do you believe we do to the 24 to get 12? And the rule you come up with has to be the same thing that you do with the 24 to get 4. And I'll give you a hint. There are 2 identical items here, and there are 3 identical here. Ashira, do you know?
So do you divide it by like how many different like same letters?
Factorial. We divide by 2 factorial. There are 2 identical items. It turns out the rule, and we don't need to prove this, the rule is you divide by 2 factorial. If there are 3 identical items, you divide by 3 factorial. 3 factorial is 6. I guess if there were 4 identical, you'd divide by 4 factorial, but then you'd just get 1 in this example. So this is the rule for identical items. In other words, well, we'll get to this in a second. If you're going to arrange a number of items and some items are identical, in other words, they appear more than once, you divide by the factorial for each of those numbers of extra, for each of those numbers that tell you how many times that thing is repeated. So if one item is repeated A times and another is B times and another is C times, this is what you would do. In other words, my cookie conundrum here, the number of unique ways that I could eat these cookies would be 9 factorial, but then I would have to divide that by 3 factorial because there are 3 indistinguishable snickerdoodles. They're indistinguishable in terms of the order in which I eat them. Right? There's 2 M&Ms that are identical and 4 chocolate chip that are identical. That's how you would answer that question. And of course, if you put that into your calculator and you went divided by, you would either need to put that in brackets or divide by 3 factorial, divide by 4 factorial, divide by 2 factorial. You know, this problem, how many cars do we have? 11? Would be 11 factorial divided by 4 factorial, also divided by 4 factorial, also divided by 3 factorial. It's a rule. It's a formal rule. It's more abstract. It's not a concrete thing. We're not going to try to reinvent this rule each time. That's what we did with all of the arrangements in the warm-up. So, example 4. How many arrangements of the letters of the word calculus are possible? Well, there's 8 letters. So you would say 8 factorial. Except of those 8 factorial, some are going to have this u here and this u here. And some of them will have those 2 u's switched, which is not different. Which is why we have this rule. You have to divide by, and I want to give you a piece of advice here. Just maybe, and all I have for my own frame of reference is what goes on in my head. I don't know how you think. But I don't think I'm abnormal. Well, I don't think I'm that different in terms of how I think from most people. And I find if you just look at that word and you start counting the identical items, it's easy to make a mistake. So I would literally go left to right, and I would say, I have a C. Oh, wait, I have 2 C's. No more C's, so I need to divide by 2 factorial. And then I would move on to the A, and I would cross it from the list and say, well, I only have 1 A. I don't need to worry about anything. I would move on to the L. I have 2 L's, and I cross them off. That's 2 factorial. I have 2 U's. That's 2 factorial. And the S. You know, I'm just saying I think you need to come up with a systematic way that you're not going to make mistakes. So it's 8 factorial over 2 factorial, 2 factorial, 2 factorial, which is 7 factorial. We've encountered situations like this before. I will explain to you why it's 7 factorial, but the reason it's 7 factorial in general has nothing to do with how we solve the problem. It just happens to be equal to 7 factorial. And the reason it's equal to 7 factorial is 2 factorial is 2. So we have 8 factorial over 2 times 2 times 2, which is 8 factorial over 8. And 8 factorial is 8 times 7 times 6, all the way down the line, so the 8's cancel and you're left with 7 factorial. So this is a case, again, where I like it and I don't like it. As part of a numerical response question, you might be given this question and told the number of arrangements of the letters of the word calculus is A factorial. And then you have another question. The number of arrangements, the number of ways you can eat these cookies is this number. And you might, as a student, be writing the exam saying, how on earth is it a single number factorial when I have repeated items? It just turns out to be 7 factorial. Okay? It's a matter of circumstance. Now we're going to look at what we call pathway problems. Jillian is walking from her home, which is H, to her school, which is S. And we can imagine these as being city blocks, maybe. Doesn't matter. She's not allowed to hop fences and cut corners and cut through people's yards. She has to stay on the sidewalks or the roads or whatever you want to call them. And there's another condition here. She always has to get closer. She's not allowed to, as my mom would say, dawdle. You have to come straight home or straight to school. She's not allowed to do this. Right? I mean, if she were allowed to do whatever she wanted to, then there's no answer to this question. So she always has to be getting closer to the school. And what becomes important here, and this might have been what I mentioned to you earlier, that your junior high math teacher might give you this to solve just to keep you busy and quiet for the day. you're not going to try to trace these out. If you tried to trace these out, well, good luck, okay? What you're going to do is make the observation that if she has to get closer to the school, she can only move this way, and she can only move this way. That's it. So she has to move, I'm going to go with left and up. If you want to use north and west because you think you're looking at a map, that's fine. She must move left and up all of the time. So she could take the following path. Would you agree that that is a path? She could take the following path. She's strayed a little bit off the sidewalk there, but that's okay. And would you agree those are two different paths? Okay. If she took this green path one day and she wanted to tell you the path she took without drawing it, she could write the following. Do you catch my drift? That these letters, the order of these letters, are the green path. And if she wanted to describe to you without drawing it what the blue path is, you would look at L, 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 1, 2, 3, 4, up, up, L, up, up. So just double check my letters and make sure they're matching my paths. Does that make sense? Okay, so that means that the number of different paths are the number of different ways you could arrange those letters. Each arrangement of those letters is a unique path. So we turn the question into this. How many ways, what do we have? 1, 2, 3, 4. We have 4 ups. And 1, 2, 3, 4, 5 lefts. And it doesn't matter, there we go. It doesn't matter what the order is. What matters is that no matter which path you take, you will be moving up 4 times and you will be moving left 5 times. So the question becomes similar to how many arrangements of the word calculus are there? How many ways can you arrange these letters? Well, the answer is 9 factorial over 4 factorial, 5 factorial. It does occur to me, we didn't really get an answer to the last question. Is 7 factorial, is that the 5040? Okay, so the answer to the calculus problem was 5040. Let's get a numerical answer here. 9 factorial divided by 4 factorial, which is 24, divided by 5 factorial, which is 120. I would only ever recommend doing this if you were positive about those, okay? I just don't like poking around in the factorial thing. I get, is it 126? Yeah, I get 126. Depending on how you look at it, surprisingly few. You might think there would have been more, especially when you see that 9 factorial. There is another way to do this problem that, and I only mention this because some people may end up finding themselves taking probability theory in a math class. And there's something we're going to learn about on Thursday called Pascal's triangle, which can be used to solve this. They teach a lot of probability theory in 30-2. So if you find yourself in a 30-2 class or you find yourself in a post-secondary class, there are other ways to do this problem. We might talk about one more tomorrow, but we'll see. Any questions with that first pathways problem, 5A? All right. How many ways to get from A to B if you must always move closer? Well, this is not just a rectangular grid. We can't do it the way we did the previous problem. But I'm going to ask you to add in here point C. And with a little reflection, everybody, you should understand that if you're always getting closer to B, and you have to arrive at B, never mind getting closer. If you have to arrive at B, you must pass through C. There's no other way. So what you need to do is go from A to B and, nope, sorry, you need to go from A to C and from C to B. You need to do two things. You need to put on a pair of pants and a shirt, figuratively speaking. You need to do the fundamental counting principle. So how many ways to go from A to C? Well, right, down, down. We have to arrange RRR, D. Which means it is 7 factorial over 3 factorial, 4 factorial. We'll get an answer in a bit, okay? I think it might be 42. Nope. I think it might be 35. Multiplied by, because it's not that you can go from A to C or C to B. You have to do both. It's a multiplication thing. Here I need to go down, right. So that's down, right, which is 4 factorial. But you have to divide by 2 factorial. So, and I'm sorry again, 35 was the first part? Pretty sure this is 6. And that works out to 210. And that's the answer to the question. Any questions with that final example? Okay, so this is what I meant by a short lesson. You've got 20 to 25 minutes-ish. You have questions dealing with, and these are in your handout, I think. Yeah. These are questions dealing with more restrictions, more conditions, repetitions. I think on page 18, those are exclusively pathway problems. And if you look on page 20, 21, and 22, there's just boatloads of permutations problems. Tomorrow we're moving on to combinations, which means order is not important. The number of ways that Bobby Bear could get dressed, that was a combination. Because he just picked out that pair of pants and that shirt. Didn't matter the order he picked them. So get started on that. I will come around and help you when you need it. And Anna, are you here tomorrow?
No.
So this is your last day. Okay. Everything I give you will have to be electronic. I have not had time to print anything out. But I will record tomorrow's lesson. I will record Thursday's lesson. I will get all of the review materials for this unit on your Google Classroom. And
Do you have just normal paper copies of them?
oh, I can do that, yeah. And then I will do that as well.
Perfect.
Okay, let me do that right now, otherwise I will forget.
Can I go just make a phone call?
Yeah, of course.